So, good evening, class. Welcome to today we'll be starting with a revision from last class based on the assignment that was given to the class. So we had two questions to solve. The first one being that to calculate how many atoms are contained in 2 grams of hydrogen gas. Now, some people tried. Yes, I saw the assignment. They did try, but this is what we expected to do. We do remember that the rule is 1 mole of every atom or 1 gram of every atom or 1 molecule of every atom is the same thing as 6.02 times 10 raised power 23. And the question, we're given the atomic mass of hydrogen, which is 1. So that one atom is 17 as 6.02 times 10 raised power 23. Then bringing in the mass, which is 2 grams, and what we are looking for, we represent that with x, cross multiply. Our final answer will be 12.04 times 10 raised power 23, or 1.204 times 10 raised power 24, if we bring decimal point forward. And the second question was, how many molecules of oxygen are contained in 0.2 moles of oxygen gas? Same thing, we're given the atomic mass of oxygen is 16. So 1 mole equals 16 grams equals 6.02 times 10 raised to the power 23. We bring in the value we are looking for, which is 0.2 moles. We get an equivalent to x. We cross multiply, and then what we have would be 0.075 times 10 raised to the power 23. So I'll be sharing this as a correction so we can go and check up what we did. Now, today's class would be a totally different topic. We're focusing on atomic structure. So under atomic structure, what we'll discuss would be particulate nature of matter, atoms, molecules, and ions, Dalton's atomic theory and its modifications, relative atomic mass, and relative molecular mass, mole and molar mass, and then empirical formula, percentage by mass, and molecular formula. So move ahead to particulate nature of matter. What's particulate nature of matter? I believe that we discussed this before, if not in this previous classes. There we see that matter is made up of discrete particles, which are atoms, molecules, and ions. Now, what are atoms? Atoms, the word atoms comes from the Greek word, or is a Greek word that actually means something that is indivisible, something you cannot break down. Now, they did not start using this word to refer to atom itself until the 19th century, when John Dalton actually brought out his research, and where he actually found out what an atom is. Now, based on that, we have a definition of an atom being the smallest particle of an element that can take part in a chemical reaction. The smallest part, the smallest dust, the smallest thing, the smallest speck of an element that can take part in a reaction on its own is an atom. Now, what about a molecule? We have to take note of the difference between an atom and a molecule. A molecule is the smallest part of any substance or a substance that can exist alone and can still retain the chemical properties of the substance. Now, we did say that atoms are the smallest element, are the smallest particles of any substance. So examples of molecules are your oxygen molecule, your hydrogen molecule, and then now these molecules exist in different states. They could be one atom, they could be two, they could be three, when we talk that one atom is called monoatomic atom. Example of that is neon. Neon exists singly on its own, doesn't have any pair, and just like that, it is a molecule on its own. And we could still call that an atom. An example of an element that has or exhibits or has two atoms in itself is hydrogen. Even oxygen too exists in pairs of two sometimes, oxygen molecule. And that type of atom that exists in pairs of two like that, they are called diatomic atoms. And it could still go up to 3, 4, and above. For 4 and above, they are called, when we have atoms paired in 4s or 5s or 6 or 8, they are called polyatomic atoms. Example of this is phosphorus. Phosphorus gets paired in 4, and that is how it exists in nature. Example, oxygen could be diatomic and still be triatomic. That especially is an example called ozone. Yeah, ozone. The ozone itself has 3 atoms of oxygen that are combined, unlike your oxygen molecule. But notice it is still the same element. Now, the ability of these atoms to exist, having 1, 2, 3, and above atoms combined to them, is called atomicity. Now, what is atomicity? Atomicity is simply defined as the number of atoms in each atom. So in our previous slide, we saw hydrogen existing as a diatomic atom or diatomic molecule, sorry. We also saw oxygen, yeah, being diatomic, and we say it could still exist as triatomic in case of ozone. So the ability of these elements to exist in these different states or as molecules having different numbers of atoms is called atomicity. Now we'll move to ions. What are ions? Ions are atoms or group of atoms which possess electric charge. Now, the charges could be positive or negative. When the charge is positive, it is called an anion. Now, for it to attain that positive nature, it has to have given off an electron so that it can now attain its octet configuration. We'll talk more about this in our subsequent class. And so we have an example here, sodium, yes. So for sodium to have attained that plus, that positive state, it has given off 1 electron. Now we have those that are negative, they are called cations. Example is chlorine. Now for chlorine to attain that negative status, to become a cation, it must have accepted an electron. When you accept, you become negatively charged. When you give out, you become positively charged. So let's take note of the difference. And notice that these anions are actually elements that single elements that now have charges. Now, we also have what we call radicals. Radicals are actually the group of atoms with charges. Example here, we have hydroxide ion, OH minus. It's oxygen and hydrogen combined together. That would have been what you have called a molecule or a compound, but then it's not having negative charge. And we have ammonium ion too, having a positive charge there. So we would have called this a compound, but now because it has a charge, it is a radical. Recall the difference. Ions are atoms, yes, or group of atoms that have electric charges. But most of the time we refer to just single atoms as ions. Then when we now want to talk about the group of atoms, when in case of this hydroxide and ammonium, we refer to them as radicals, although they are all ions. Now, let's now talk about Dalton's atomic theory. remember, we said that it was until when Dalton postulated his theories, when he brought up his research, that he started calling atoms or referring to these small elements, this indivisible particle as it was, as atoms. So what are the postulates that Dalton brought up in the year 1808? The first one is that all elements are made of small indivisible particles called atoms. He said all elements, no matter what the element is, they're made up of atoms which are indivisible. Well, from the definition of what atoms are, or their source name, we see that they are referred to as indivisible back then. So he also said that atoms can neither be created nor destroyed, that you can never destroy atoms. Since they are indivisible, they can never be destroyed, and you cannot create them on your own because they are natural, according to him. And he also said that atoms of the same elements are exactly alike. They are no different. They always look alike. Once you see chlorine, it is chlorine. It cannot exist in a different way. It has to be chlorine the way it is. And he also said that when atoms combine with other atoms, they do so in simple ratio. They cannot be bigger than they are. He was looking at, say, water. Water is just H2O. That's two atoms of hydrogen, one atom of oxygen. He says that is how simple they come. And he also said that all chemical changes result from the combination or the separation of atoms. Sad to say, these postulates, some of them were actually corrected. Not that they are completely wrong, but some adjustment had to be made after further research were carried out by different scientists. So let's talk about these modifications to Dalton's atomic theory. Remember, the first one, he said that atoms are made of small particles that are indivisible and they're atoms. Well, Rutherford brought up a theory that actually proved it wrong. When he found out that these atoms were made up of particles which are protons, neutrons, and electrons. So if atoms possess protons, neutrons, and electrons, that means they can't be divided. For you to be able to see that these things exist in them, that means they're actually divisible. So that broke down his first postulate. The second postulate means that atoms can neither be created nor destroyed. Was also cancelled because it only holds for ordinary chemical reactions. But when you talk about reactions that include fission and fusion, here we're talking about radioactivity. Radioactivity is the spontaneous decay of radioactive elements. We'll talk about this subsequently also. Now, when radioactivity occurs, specifically fission, fission is the breaking down of a radioactive element. Now, this is the same process that is used in creating these nuclear bombs. When they are forced to break, when they are forced to divide, it causes an explosion. Now, for you to be able to force it to divide or break in the first place, that means it is divisible. And that also means that they can be destroyed. And when we talk of fusion, which is bringing together of different elements, which is also a radioactive process, that means you are creating elements there or creating new materials there. Now, so the second one too doesn't hold. Now, what about the third one? Atoms of the same element are exactly alike. Well, that was correct until when they found out what we call isotopes. So isotopy is the ability of an element to exist in different states, having the same atomic number, but different mass numbers. Say, for example, carbon. Carbon has atomic number of 6, but it can also have a mass number of 12 and a mass number of 14. So this is the same carbon, but now having different isotopes which possess different mass numbers. So that means that they cannot all be exactly alike, mostly when they have these isotopes. We also have uranium and other elements that have isotopes like this. They have 2, 3, or thereabout elements having different mass numbers, but the same atomic number. Now, what makes them have these different mass numbers is because their neutron number differs, but they'll have the same number of protons. Where their neutron number differs, then they'll have different mass numbers, because the mass number is the addition of your neutron and your electron. Now, what about the fourth postulate? When atoms combine with other atoms, they do so in small ratios. Well, after the discovery of larger molecules like your starch and your proteins and your fats and oil, which are long chains. For example, your fats is made up of long chains of hydrocarbons that are formed. We are talking of 10, 15, 20, I mean, very long chains of carbon and hydrogen bonds. So those are not simple ratios. And then talking about your proteins, they are made up of amino acids that are long chains. So this proves that they do not always combine in small ratios. Although for inorganic compounds like your hydrochloric acid, like your sodium hydroxide, like your sodium chloride, for these ones, they combine in small ratios. But for organic compounds, they usually combine in very long and large ratios. Now, that is for the fourth one. Well, the fifth one still holds, because for chemical change to actually occur, there has to be either a breaking down or coming together of different atoms, as the case may be. So that's Dalton's atomic theory and the modification that were made to it by other scientists. Now we move to relative atomic mass. What is relative atomic mass? It is the number of times the average mass of one atom of that particular element in consideration is heavier than 1/12 the mass of one atom of carbon. Now, why are we talking about carbon? Carbon, it was set as the basis for comparison with other elements, carbon-12 specifically. Now, comparing these elements, the atomic masses of these elements with that of carbon, they compare, okay, what is the weight of this particular element, say hydrogen, compared to carbon? That will determine the relative atomic mass. Remember, based on English, when we talk of something being relative, it's comparison between two things. So they are comparing these elements to carbon. Now, today, we do not go by dividing the atomic mass of this element by 1/12 of carbon. What they use to determine the relative atomic mass is called the mass spectrometer. So the mass spectrometer gives accurate measurement of the atomic masses of different elements. Now, the use of these has actually proven that atoms of most elements exist in more than one form, which is known as isotopes, as we discussed earlier. Now, we have an example here of chlorine 35 and chlorine 37. Now, if we do know our periodic table well, we would know that chlorine has an atomic number of 17. But here it can atomic mass or mass number of 37, or its original form having 35. So the only way we're able to really define and find out that this exists is using the mass spectrometer. Remember, the atomic mass of an element is the number of times the average mass of one atom of that element is heavier than 1/12 of the mass of one mass of carbon-12, the atom of carbon-12. Now, as we said about isotopes, they are elements which have the same atomic number or different mass number, and we've mentioned a couple of examples. Now, what about relative molecular mass? Now, for, for relative molecular mass, this is the number of times the average mass of one molecule of an element is heavier than 1/12 of the mass of one atom of carbon-12. So here now we're talking about molecule, not atom. But both are being compared with the mass of carbon-12. Now, for you to get the relative atomic mass of an element or a group of elements, you need to add up the masses. You need to add up the masses of the different atoms that make up this molecule. And by adding them up, you will get the relative molecular mass of that molecule. Now, the formula here shows how we can actually do this. You see there, says relative molecular mass or molar mass is equal to the sum of the number of atoms times the relative atomic mass or mass number of each atom. Now, what do we mean by this? Let's look at this example here. The first question here is calculate the relative molecular mass of limestone. Limestone is calcium trioxocarbonate. So it contains calcium, contains carbon, and contains oxygen. We notice there in the bracket, the atomic masses of each of these elements is given. Calcium has atomic mass of 40, carbon 12, and oxygen is 16. Now, for you to be able to calculate the relative molecular mass, you need to multiply the number of each atom in that compound times their molar mass. Times their atomic mass. Sorry about that, please. Now, we see that of calcium. We have only one atom of calcium here. Now, let's take note of this. When you're trying to calculate this, even if you do not see any number written as a subscript or as at the base of each element, the fact that the element is there, it means it is 1. So that's why we have 1 times 40 for calcium, because we have only one atom of calcium there, and its atomic mass is 40, plus 1 times 12, because we have only one atom of carbon, and the atomic mass is 12, and then 3 times 16, because we have 3 atoms of oxygen. I believe we can see the 3 there beside oxygen, times 16. That will give you a total of 100. So we are calculating the relative molecular mass of a molecule or a compound. It does not have any units. Now, see another example here. The second one, calculate the relative molecular mass of ammonia. Ammonia is nitrogen and hydrogen. Atomic mass of nitrogen is 14. Atomic mass of hydrogen is 1. Now, because of that, we have 1 times 14 plus 3 times 1. Remember, hydrogen here has 3 atoms, so that we have 3 times 1, so that gives you 17. Now, this same method we apply in calculating or determining the relative molecular mass is what we still use in determining molar mass. However, the difference is that molar mass has a unit, which is gram per mole. So I remember we talked about this in the last class, calculating the molar mass of a few compounds there. So we see it still featuring here. Now, going to mole. What is mole? So 1 mole of a substance is the amount containing as many elementary entities as the number of atoms in exactly 12 grams of carbon. We established that 1 mole of every substance is the same thing as 6.02 times 10 raised to the power 23 particles of that substance. I would say this is the Avogadro's constant. So that means 1 mole of an atom, 1 mole of a molecule, 1 mole of an ion contains exactly 6.02 times 10 raised to the power 23 atoms, molecules, or ions of that particular substance we are talking about. Remember, we also compared this number to, say, 12x is something as a dozen. half or 6 eggs, same thing as half a dozen. So it's just like that. 1 mole is the same thing as 6.02 times 10 raised to the power 23. Please, let's keep that in the back of our mind, because questions like this or having something like this would feature in exam examinations. So that moves us to the next part, which is percentage by mass. Now, you calculate the percentage by mass of elements in a compound. And by the time you calculate this, it helps you determine, oh, what's the percentage of this element in this compound? And it is, let's see how we calculate it, because we actually have a formula for calculating it. See the example here. We have calculated percentage by mass of nitrogen in triosonitrate 5 acid, which is HNO3. Now, see the molecular formula there being HNO3, yeah? So we have 1 mole of hydrogen, 1 mole of nitrogen, and then 3 moles of oxygen atoms. So how do we calculate this? We see there we have 1 times A, which is the atomic mass of hydrogen, then 1 times A of nitrogen, 1 times the atomic mass of nitrogen, which is 3, which is 1 times 14, and then 3, which is number of oxygen atoms, times the atomic mass of oxygen, which is 16. So that has 1 times 1 plus 1 times 14 plus 3 times 16, and that gives us 63 grams. Now that is for obviously the atomic, that's the relative molecular mass or the molar mass of the entire compound. So now, for us to now get the percentage by mass, see it here. Yeah, I say, okay, to calculate the percentage by mass of nitrogen, see what happened there? We now pick out the atomic mass of nitrogen, which is 14, divided by 63, which is the relative molecular mass, times 100. So that gives us 22.2%. So if you bring out all of these numbers, you bring out that of hydrogen, bring out that of oxygen, you will be getting the total of 100, because it must always give you 100%. And to tell you the percentage of each element in the compound. Now that's one example there. So we move to another part, which is empirical formula and molecular formula. Now, we did say that percentage by mass gives you the percentage of each element in the compound. But what empirical formula will do for you is it will give you an analysis of each of these elements, their ratio. That's what it will give you. To give you the ratio of each of these elements in the compound. Now, let's see an example of this. The example here is find the empirical formula of a compound which on analysis yields the following: 2 grams of carbon, 0.34 grams of oxygen, of hydrogen, and then 2.67 grams of oxygen. We have the atomic masses: C equals 12, O equals 16, and H equals 1. Now, this is how it is solved. You see, so remember here we have carbon as 2.0 grams, hydrogen as 0.34, and oxygen as 2.67. So we divide all of these numbers by their atomic masses. That's the first thing you do. Even if it's the percentage you are giving or the masses you are giving, you divide each of these masses by their atomic mass. Now, after dividing 2.0 by 12, 0.34 by 1, and 2.67 by 16, we have 0.172 and 0.17. Now, after you've gotten these numbers, the next thing you do is you divide all through by the smallest of these numbers. Now, what's the smallest number between 0.172 and then 0.17? Obviously, it's 0.17. So you divide all through with 0.17. So that's why we have the answer as 1, 2, and 1. Now, when you are trying to calculate on your own, you might get decimal points. Please, these elements do not exist in decimals, so you would have to round up. So let's say you are getting something like 1.99 whatever, you must have to have round up to 2. If you have something like 2.30 whatever, if you round up that 3, you'll be getting 2 still, because you cannot round up. You can only round off numbers that are less than 5. So with that, we have the empirical formula of the compound being C, because carbon there is only 1, H2, because we have 2 atoms of oxygen there, and then 1 atom of 2 atoms of hydrogen and then 1 atom of oxygen. So as we said, the empirical formula helps you determine the ratio of each of these elements. So that's why we're able to find out that the ratio here is C1 H2O1. But you don't have to write the 1, so that's why you just write it as CH2O. Now, we talked about molecular formula. How do you not get the molecular formula? For you to get the molecular formula of this compound, what you now do is you get the atomic mass of, or the molar mass of the compound generally, and then that of the same compound as it is given here as the or whatever you are given, whatever you are given. Now, you will now divide this number. So here we are giving that the number is actually 30. But now we now get the molar mass to be 60. So dividing it, we have 2. So that means that you now multiply that 2 with each of the elements as represented in the empirical formula. Notice the empirical formula, we have C1H2O2. So multiply all through with 2. What you have will be C2H4O2. And if you are good with arranging these elements properly, what you have will be CH2COOH. We'll still discuss this further, not now though. So we have another example here. Determine the empirical formula of an oxide of nitrogen containing 70% of oxygen. The relative molecule of the oxide is 92. So deduce its molecular formula. So they said that oxide of nitrogen. So and they said oxygen is 70%. Now, obviously, remember I've told you guys before that it has to give you 100%. So if oxygen is 70%, that means nitrogen has to be 30%. So that's why we now put 70 and 30. Atomic mass of oxygen is 16. Atomic mass of nitrogen is 14. So dividing through, we have 4.38 and 2.1. Remember, you divide next with the smallest number. So dividing with smallest number, see they have 4.38 divided by 2.1 is 2.1. Obviously, excuse me, and then 2.1 divided by 2.1, you have 1. So the empirical formula will be NO2. Why? Oxygen is 1 and then oxygen is 2 and then nitrogen is 1. So N1O2. Like I said, you cannot write the 1. So now, to now get the molecular formula, remember, we have been given that it has a relative molecular mass of 92. So we divide that with the molar mass of this compound. So dividing that with the molar mass of the compound, we have 92 divided by 46, which gives us 2. Now, when you get this number, remember I said you now multiply all through with that number. So we have 2 times N2 times O2. So that gives us, well, 2 times N times O2, that gives us N2O4. So empirical formula gives you the ratio, while molecular formula will tell you the exact number of these atoms in the compound. So after you've gotten your empirical formula, you should to derive your molecular formula. So that's that for empirical. let's take questions now. Do we have any question based on what we've discussed so far? Is there any question? Okay, so if there's no question, or if there are no questions, we'll be leaving assignments later on for you guys to carry out and to practice what we've discussed so far. Remember, we've been able to talk about the Dalton's atomic theory, his postulates, and then the modifications that were made to them. We've also been able to distinguish between atoms, ions, and molecules. And we also talked about radicals, which are this group of atoms that have charges. And so far, we've been able to talk about the relative atomic mass and relative molecular mass. So you use relative atomic mass to find the relative molecular mass. And we said the difference between relative molecular mass and molar mass is that molar mass has units, while relative molecular mass do not have units. And the mass of the unit is actually grams per mole. And we're able to see how to calculate the empirical formula, percentage by mass, and we've also been able to see how to get the molecular formula. Yes, I just saw your message. Yes, it will be sent. It will be sent to you. There's no problem. We will send the slide to you so that you can actually still go through it on your own. Yes, so that would be done. But still, if you have questions, you can still ask. So you are welcome. So we'll forward the slides to you guys so that you can check it out and study it. Okay, no question for now. That's fine. It's no problem. It's all right. So I believe would take it as a wrap. Yeah. If there are no questions. But please, when we do give assignments, it will be very nice for us to do these assignments because it helps us know, okay, this is how far you understood, and we'll be able to make corrections. Like we were able to make corrections at the beginning of the class, so you see how to solve the questions on your own. Because many times, except if other topics bring us back to this question, it will be quite difficult for